Top 1. The Damascus Blade. The Damascus Blade. In 1187, during the Battle of Hattin in the scorching hills near Tiberias, Crusader knights recorded an encounter that unsettled even seasoned warriors. Chroniclers described Muslim blades that sliced through chainmail as if it were woven cloth. One account claimed a silk scarf dropped upon the edge of such a sword would fall in two pieces under its own weight. The detail was dismissed for centuries as poetic exaggeration. But when surviving blades were examined under modern microscopes, the myth became harder to ignore. These weapons were not ordinary steel. They were something else, and they should not have existed in that form at that time. Known today as Damascus steel, these blades display a flowing, water-like pattern across their surface, a series of rippling lines that seem almost organic. Metallurgical analysis reveals a matrix of high-carbon steel interlaced with microscopic carbide structures. Under scanning electron microscopy, researchers observed nanotube-like formations and cementite nanowires embedded within the blade. These structures significantly enhance hardness and edge retention. Tests on surviving specimens suggest edge durability exceeding many contemporary stainless steels. What makes this more unsettling is the timeline. The methods required to control carbon content and cooling rates at such precision were not formally understood until centuries later. The forging process was not simple pattern welding. It relied on a specific raw material known as wootz steel, imported from southern India. The steel ingots were heated carefully, never hammered at high temperatures, preserving internal crystalline patterns. A single miscalculation could destroy the internal structure. The result was a blade that combined flexibility with cutting power, capable of bending several inches without snapping and returning to form. Modern blacksmiths have attempted to replicate the process using historical descriptions. Many have failed. The exact composition of trace elements, including vanadium and molybdenum, appears to have played a role, yet the original ore sources are depleted. By the 18th century, the method vanished. Workshops closed. Trade routes shifted. Political instability disrupted the transmission of knowledge. European scientists studied surviving blades but could not reproduce the same microstructure consistently. Some concluded that subtle impurities in the original ore were critical. Others suggested the cooling cycles were tied to regional climate conditions no longer replicable. Whatever the reason, the chain of knowledge broke. The formula was not written down in full. It lived in hands and memory. When those hands disappeared, so did the steel. In recent decades, classified defense laboratories have studied historical Damascus blades, reportedly exploring applications for advanced cutting tools and military-grade alloys. Few findings were made public. Independent researchers who requested detailed metallurgical data encountered redacted documents and restricted access. Museums allow observation, but rarely full sampling. The material exists. It can be tested. Yet the complete reproduction remains elusive. If a civilization in the 12th century could produce steel with nanoscale precision without modern instruments, what does that suggest about the level of empirical knowledge they possessed? And more importantly, how many other materials were perfected through tradition and then erased when empires fell? The Damascus blade is not merely a weapon. It is evidence that technological peaks do not always move forward. Sometimes they collapse. Sometimes they vanish. And sometimes they leave behind only patterns in the metal. Reminders that history may not be the straight line we were taught to believe. Top 2. The wootz steel. The wootz steel. In 300 BC, in the furnace-lit workshops of southern India, blacksmiths were producing steel ingots that would travel thousands of miles across deserts and oceans. These ingots, small and unremarkable in appearance, were sealed inside clay crucibles and heated to temperatures exceeding 2,500 degrees Fahrenheit. Merchants transported them westward to Persia and the Levant, where master swordsmiths transformed them into the legendary blades, later known as Damascus steel. But long before the rippling patterns appeared on finished swords, the true mystery had already taken shape inside those crucibles. The steel itself possessed qualities no other region on Earth could replicate, and no detailed manual explaining its creation has ever been found. Wootz steel was not simply iron mixed with carbon. It was the product of a closed crucible process that allowed molten steel to absorb carbon evenly while preventing oxidation. Iron ore was combined with plant matter, possibly bamboo or leaves rich in carbon, then sealed in ceramic containers and heated for extended periods. As the contents liquefied and cooled slowly, they formed a high-carbon steel ingot with a uniform internal structure. Modern analysis of surviving wootz samples has revealed something extraordinary. Embedded within the matrix are microscopic carbide particles aligned in distinct patterns, creating natural reinforcement at a nanoscale level. These carbides contribute to exceptional hardness while preserving flexibility, a combination difficult to achieve even with controlled industrial processes. In 2006, materials scientists examining historical wootz fragments under high-resolution electron microscopes detected carbon nanotube-like structures within the steel. These formations are typically associated with advanced nanotechnology, yet here they were in material forged more than 1,000 years ago. The presence of trace elements, such as vanadium, appears to have played a critical role, influencing how carbides precipitated during cooling. What complicates matters further is that these elements were not deliberately isolated in ancient times. Their inclusion depended entirely on specific ore sources found in limited regions of India and Sri Lanka. When those mines were exhausted or abandoned, the chemical balance that made wootz unique may have disappeared with them. By the 17th century, production of true wootz steel declined sharply. Political upheaval, colonization, and the disruption of trade routes fractured the network of craftsmen who understood the crucible method. European metallurgists attempted to reverse engineer the steel, melting and remelting fragments in laboratories. They succeeded in producing high-carbon steel, but not the same patterned carbide alignment. Replicas often lack the distinctive internal microstructure that gave original wootz its mechanical superiority. Some historical accounts suggest the knowledge was deliberately guarded within family lineages. Recipes were memorized, not recorded. Apprenticeship required years of observation. When a master died without a successor, part of the process died as well. Later British industrial reports referenced Indian steel of unusual resilience, yet offered no explanation for its manufacture. Colonial administrators focused on mass production rather than preservation of traditional methods. The crucibles fell silent. If wootz steel depended on a precise combination of ore chemistry, carbon infusion, temperature control, and cooling rate, then its disappearance was not inevitable. It was contingent. A fragile system collapsed under political and economic pressure. The material that once fed the most feared blades of the medieval world faded into metallurgical legend. If the foundation of Damascus steel originated in these crucibles, then the mystery runs deeper than decorative patterns on a sword. It lies in a lost understanding of phase transformation, carbon diffusion, and impurity control centuries ahead of its time. And if such control existed once without modern theory, how many other empirical technologies were refined through repetition, only to vanish when history shifted direction? Top 3. The Ulfberht sword. The Ulfberht sword. In 873 AD, along the banks of the Rhine River, a Frankish chronicler described a raid unlike any before it. Norse warriors carried blades that did not shatter against shields, did not bend permanently under stress, and did not splinter along their edges after repeated impact. One captured sword bore a name stamped deep into its fuller, Ulfberht. The inscription appeared on dozens of blades recovered centuries later from burial sites across Scandinavia and Central Europe. At first glance, they seemed like prestige weapons, forged by a master smith. But when modern metallurgists place fragments under spectrographic analysis, the numbers did not align with the technology of the era. The steel was too pure, and it should not have been possible in 9th century Europe. More than 170 Ulfberht swords have been discovered to date. Not all are equal. Some are crude imitations, but a subset stands apart. These authentic specimens contain carbon levels reaching up to 1.2%, comparable to modern high-grade tool steel. More striking is the absence of slag inclusions. Medieval European bloomery furnaces typically produced iron riddled with impurities due to insufficient heat and limited oxygen control. Removing slag required repeated hammering and folding, yet complete purification was nearly impossible. The Ulfberht blades show almost none of the structural contamination expected from bloomery production. Achieving such purity would require sustained temperatures above 2,700 degrees Fahrenheit, conditions normally associated with blast furnaces that would not appear in Europe for another 3 centuries. Microscopic examination reveals a homogeneous internal structure, lacking the layered inconsistencies of conventional Viking swords. The blades are strong, yet flexible, capable of absorbing shock without fracturing. Experimental reconstructions using traditional Scandinavian furnace techniques failed to replicate the metallurgical profile. The question emerged, where did this steel originate? Some researchers propose that raw crucible steel from Central Asia, possibly related to wootz production, traveled north along the Volga trade routes. If so, the Vikings were not simply raiders, but intermediaries in a vast metallurgical network stretching thousands of miles. By the 11th century, the true Ulfberht blades vanish from the archaeological record. The imitations persist, often with misspelled inscriptions, suggesting demand outlived supply. Political shifts, the collapse of Eastern trade routes, and changing power structures in the Islamic world may have severed access to the high-quality steel source. Without the imported material, European smiths returned to bloomery iron, and the advanced metallurgy faded. The inscription itself adds another layer of intrigue. Was Ulfberht a single craftsman, a monastic workshop, a brand? The precision of the lettering implies organized production, yet no documented forge bearing that name survives in historical archives. Some historians believe the blades were produced under ecclesiastical authority, perhaps in a monastery with access to rare materials. If so, why was the method never institutionalized? Why did it disappear instead of evolving into standard practice? Modern laboratories have studied these swords extensively. Access to certain museum specimens is restricted, citing preservation concerns. Detailed compositional data are occasionally withheld. Military researchers have expressed interest in ancient steel microstructures for modern applications, though no formal reports link directly to Ulfberht replication efforts. If Vikings wielded steel centuries ahead of European metallurgy, it challenges assumptions about technological diffusion. The Middle Ages are often portrayed as stagnant, yet here is evidence of advanced material science hidden within burial mounds. And if such steel depended on fragile global trade and specialized knowledge, its disappearance suggests how easily technological peaks can collapse. The Ulfberht blades do not rewrite history outright, but they expose gaps in it. And when the steel itself contradicts the accepted timeline, the silence surrounding its origin becomes as significant as the metal that remains. Top 4. The Roman concrete. The Roman concrete, in 79 AD, as Mount Vesuvius erupted and buried entire cities beneath ash, Roman harbors along the Mediterranean coast continued to stand firm against the sea. Breakwaters, piers, and seawalls endured relentless saltwater corrosion, tidal force, and seismic activity. Nearly 2,000 years later, divers examining submerged Roman structures near Pozzuoli and Caesarea found something unexpected. The concrete was not crumbling, it was strengthening. Core samples extracted from blocks weighing several tons revealed internal crystalline formations that had grown over centuries. Modern engineers stared at the results in disbelief. The material seemed to repair itself, and that was never supposed to happen. Roman concrete, known as opus cementitium, differed fundamentally from modern Portland cement. Instead of relying solely on limestone clinker, Roman builders mixed volcanic ash called pozzolana with lime and seawater. When cracks formed and water penetrated the structure, chemical reactions triggered the growth of calcium aluminum silicate hydrates and rare minerals such as tabermarite. These crystals filled fractures over time, effectively sealing weaknesses. Laboratory simulations confirmed that exposure to saltwater accelerated the formation of these strengthening compounds. Where modern concrete deteriorates under marine conditions within decades, Roman harbor walls have endured for millennia. In 2017, a multinational research team published findings showing that Roman concrete samples exhibited increasing durability with age. The crystalline structures interlocked at microscopic levels, distributing stress more evenly throughout the material. Modern concrete, by contrast, often suffers from microfractures that expand under thermal cycling and salt intrusion. Repair requires external intervention. Roman structures appear to activate internal reinforcement when exposed to environmental stress. What unsettles material scientists is not that the Romans stumbled upon a durable formula, but that the exact proportioning methods and mixing techniques were not comprehensively documented. Vitruvius described ingredients, yet the precise temperature control during lime preparation and the sequence of combining components remain debated. Experimental recreations have achieved similar results under laboratory conditions, but scaling the process industrially has proven inconsistent. The Romans mastered a material whose behavior they may not have theoretically understood, yet empirically refined to extraordinary resilience. Following the fall of the Western Roman Empire, large-scale pozzolanic concrete production declined. Medieval builders reverted to lime mortars with significantly lower structural strength. The knowledge of hydraulic concrete was partially preserved but not fully exploited. By the time modern cement emerged in the 19th century, it followed a different chemical pathway optimized for rapid strength gain rather than long-term mineral evolution. Speed replaced endurance. Construction cycles shortened. Longevity became secondary to cost and efficiency. Recent infrastructure failures have renewed interest in Roman methods. Engineers facing collapsing bridges and seawalls have revisited ancient samples. Yet commercial construction standards remain anchored to Portland cement formulations. Integrating self-healing mineral systems requires rethinking supply chains, curing times, and regulatory frameworks. Economic incentives favor fast production over centuries-long durability. If Roman concrete truly strengthens over time, it represents more than an ancient curiosity. It suggests a lost philosophy of construction, one that prioritized permanence over speed. Massive aqueducts, domes spanning over 140 feet, and harbor installations weighing thousands of tons were built to endure generations. If a society 2 millennia ago engineered infrastructure capable of surviving ocean exposure for thousands of years, why do modern equivalents fail within a fraction of that time? Was the shift driven by ignorance, economics, or a conscious decision to accept impermanence? The harbors still stand, the crystals continue to grow, and beneath layers of salt water, Roman concrete quietly challenges the assumption that modern materials are always superior. Top 5. The Delhi Iron Pillar. The Delhi Iron Pillar. In 415 AD, in the heart of what is now Delhi, a towering iron column was erected under the rule of Chandragupta II. Standing over 23 feet tall and weighing more than 6 tons, the pillar was forged from nearly pure iron and placed outdoors without shelter. It was not coated in paint. It was not encased in protective stone. It stood exposed to monsoon rains, humidity, and air pollution for more than 16 centuries. When British engineers examined it in the 19th century, they expected deep corrosion. Instead, they found a surface almost entirely free of rust. The pillar should have decayed centuries ago. It did not. Modern metallurgical analysis reveals that the iron contains unusually high levels of phosphorus and very low sulfur content. Unlike modern steel, which typically removes phosphorus to improve mechanical properties, the ancient smelters retained it. Over time, this composition allowed the formation of a thin, stable passive film known as mesowite on the surface. This layer acts as a natural corrosion barrier, preventing oxygen and moisture from penetrating deeper into the metal. Once formed, it continues to protect the structure without external maintenance. The forging method itself remains part of the mystery. The pillar was not cast as a single molten piece. It was created by forge welding multiple iron blooms together, hammering them while hot until they fused into a seamless mass. Achieving structural integrity across such a large object required precise temperature control and exceptional craftsmanship. The consistency of the weld lines indicates an advanced understanding of heat distribution and mechanical consolidation. For comparison, modern steel monuments often rely on alloying elements such as chromium to resist corrosion. The Delhi pillar achieves similar longevity without stainless steel chemistry. Researchers from the Indian Institute of Technology conducted accelerated corrosion tests on sample fragments. Even under simulated acidic conditions, the material demonstrated remarkable resistance. Attempts to replicate the exact passive film formation have met with partial success, but recreating the long-term stability remains difficult. The environmental conditions of Delhi, including alternating wet and dry cycles, appear to contribute to the gradual strengthening of the protective layer. The metal does not simply resist decay, it adapts to its surroundings. There are no detailed manufacturing blueprints preserved from the Gupta period describing the pillar's construction. Inscriptions carved into its surface praise the king and divine protection, but they do not explain the metallurgy. Knowledge likely passed between specialized guilds of ironworkers. When political structures shifted and patronage declined, large-scale projects of this complexity ceased. Smaller iron tools continued to be made, but the art of producing massive corrosion-resistant structures faded. Colonial reports in the early 20th century documented foreign scientists requesting core samples for laboratory study. Access was restricted. The monument was deemed culturally sensitive. Detailed compositional data circulated within academic circles, but were rarely publicized widely. The pillar remained standing, visible yet unexplained in practical terms. If ancient Indian metallurgists could engineer an iron structure that survives centuries of exposure without modern alloys, it suggests a level of empirical material control that challenges simplified narratives of technological progress. The pillar is not coated, reinforced, or maintained by modern methods. It stands because its internal chemistry works in harmony with the environment. If corrosion resistance of this magnitude was achieved once through careful control of trace elements and forging conditions, why was it not industrialized later? Did economic pressures favor faster production over long-term durability? Or did the expertise vanish when centralized power fragmented? The Delhi iron pillar does not shout its achievement, it simply refuses to decay. And in that silence, it poses a question modern engineering still struggles to answer. Top 6. The Lycurgus glass. The Lycurgus glass. In 1845, deep within the storerooms of the British Museum, curators examined a late Roman glass cup known as the Lycurgus cup. Under normal lighting, the vessel appeared opaque green, but when a light source was placed inside it, the glass shifted to a deep translucent red. The transformation was immediate and dramatic, as if the material itself possessed awareness of illumination. At first, the phenomenon was attributed to impurities or aging. Only in the late 20th century did scientists uncover what truly lay embedded within the glass. The explanation was not artistic trickery, it was nanotechnology, and it existed in the 4th century AD. The Lycurgus cup, measuring roughly 6.5 inches tall, depicts a mythological scene carved in high relief. But its optical behavior is what unsettled researchers. When examined under transmission electron microscopy in the 1990s, scientists discovered that the glass matrix contains nanoparticles of gold and silver, dispersed at sizes between 50 and 100 nanometers. At that scale, metallic particles interact with light through surface plasmon resonance. Different wavelengths are absorbed and reflected depending on the direction of illumination, producing the striking color shift. Controlling nanoparticle size and distribution requires precision. In modern laboratories, synthesizing metallic nanoparticles demands careful temperature regulation, chemical reduction processes, and advanced instrumentation. The Roman artisans had none of these tools, yet somehow they achieved uniform dispersion within molten glass, avoiding aggregation that would have ruined the optical effect. The concentration of metals is measured in fractions of a percent. Too little would produce no color change. Too much would darken the glass. The balance is exact. Historical records do not describe intentional nanoparticle engineering. Roman glassmakers were skilled, but their theoretical understanding of atomic structure was non-existent. The process may have relied on empirical adjustments to furnace temperature and the addition of metallic salts during melting. But reproducing the exact dichroic effect consistently has proven challenging for modern artisans attempting historical reconstructions. Many replicas approximate the color change, but fail to match the sharp contrast observed in the original. The cup survived the collapse of the Roman Empire, passing through private collections before entering public exhibition. Detailed compositional data from advanced analysis are published selectively. Certain aspects of the manufacturing process remain speculative. Museums restrict invasive sampling, limiting full replication studies. What is known is that the glass's optical properties mirror principles now exploited in biomedical sensors and photonic materials. If Roman craftsmen unintentionally stumbled upon nanoscale manipulation, it suggests a level of empirical experimentation rarely credited to antiquity. If they did so intentionally, it suggests something far more complex, a workshop tradition capable of controlling metallic behavior at scales invisible to the human eye. The Lycurgus cup stands as more than decorative art. It embodies a material phenomenon not formally explained until modern quantum physics, and yet it was shaped, carved, and polished nearly 16 centuries ago. If ancient artisans achieved nanoscale optical engineering without theoretical frameworks, what other material secrets were embedded in objects dismissed as ornamental? How many technological insights are locked inside artifacts displayed behind glass, admired for beauty rather than studied for lost science? The cup changes color when light passes through it, but perhaps the more profound transformation occurs in perception. What seems primitive under one light reveals sophistication under another. Top 7. The Qin Bronze Weapons. The Qin Bronze Weapons. In 1974, farmers digging a well near Xi'an uncovered fragments of what would become one of the largest archaeological discoveries in history, the terracotta army of Qin Shi Huang. Thousands of life-size soldiers stood buried for over 2,000 years, each equipped with real bronze weapons. When conservators began extracting swords, spearheads, and arrowheads from the soil, they anticipated heavy corrosion. Bronze typically oxidizes over time, especially in damp subterranean conditions. Yet many of the blades emerge with sharp edges intact and surfaces surprisingly smooth. Laboratory tests revealed something unexpected. A thin layer of chromium oxide coated portions of the metal. Chromium plating, as far as industrial history records, was a 20th century innovation. Initial spectroscopic analysis detected trace chromium on the surface of several weapons. The discovery sparked immediate speculation. Had ancient Chinese metallurgists developed an early form of chrome plating? Achieving such a coating requires knowledge of chromium compounds and high-temperature processing techniques that modern electroplating would not formalize until the early 1900s. If deliberate, the technology would represent a leap centuries beyond its accepted timeline. However, deeper investigation complicated the narrative. While chromium was indeed present, researchers found it inconsistently distributed. Some weapons showed surface chromium, others did not. Further soil analysis revealed high chromium content in nearby lacquered wooden components that once formed parts of the weapon's handles and crossguards. It is possible that chromium migrated from lacquer preservatives into the bronze over centuries of burial. Yet that explanation does not fully account for the remarkable state of preservation. Metallurgical tests indicate that Qin bronze weapons were cast with unusually high tin content, increasing hardness and corrosion resistance. Additionally, the casting molds were crafted with exceptional precision, producing blades that required minimal finishing. Microscopic analysis of surviving swords shows uniform alloy distribution and tight grain structure. Some blades remain sharp enough to cut paper even today. Reproducing this consistency in large-scale bronze casting without modern temperature sensors or chemical assays presents a formidable challenge. Experimental archaeology teams have attempted to recreate Qin-era bronze using period-accurate furnaces. While hardness levels can be approximated, matching the original durability and corrosion resistance has proven inconsistent. Soil chemistry may have contributed to preservation, but the alloy itself demonstrates intrinsic resilience. The combination of tin concentration, casting technique, and possible surface treatment suggests a systematic approach rather than accidental success. The Qin dynasty was known for administrative standardization, unifying weights, measures, and script. It is plausible that metallurgical procedures were similarly regulated, yet detailed records describing weapon alloy formulations have not survived. If such documentation existed, it may have perished during the fall of the dynasty or later political upheavals. The chromium debate remains unresolved. Some researchers argue that the presence of chromium was incidental contamination. Others maintain that the concentration patterns imply intentional treatment. What is certain is that Qin bronze weaponry demonstrates an advanced understanding of alloy optimization and mass production rarely attributed to 3rd century BC technology. If ancient Chinese workshops could produce thousands of near-identical weapons with exceptional durability, It challenges assumptions about pre-industrial manufacturing limits. And if chromium or another protective process was deliberately applied, it suggests surface engineering centuries ahead of its time. The terracotta army stands silent in its underground formation, but the metal it carried continues to provoke questions. Was this simply efficient bronze casting refined through repetition? Or does it hint at metallurgical knowledge that briefly flourished and then faded from recorded history? Top 8. The Maya blue pigment. The Maya blue pigment. In the humid lowlands of Mesoamerica, where heat, rain, and dense vegetation accelerate decay, murals painted over 1,000 years ago still display a vivid turquoise blue intensity. Archaeologists working at sites such as Chichen Itza and Bonampak uncovered walls coated in a pigment that should have deteriorated long ago. Acid rain, microbial growth, and centuries of exposure should have stripped the color away. Instead, the blue remains strikingly resilient. Laboratory tests attempting to dissolve it in nitric acid and heat it to extreme temperatures failed to erase its structure. The pigment did not merely survive, it resisted destruction. Known today as Maya blue, the material is a hybrid compound combining indigo dye with a fibrous clay mineral called palygorskite. Indigo alone degrades under ultraviolet light and moisture. Palygorskite on its own is a stable but dull mineral. When heated together under specific conditions, however, the organic molecules of indigo penetrate the microscopic channels of the clay lattice, forming a stable chemical bond. The resulting composite locks the dye into the mineral matrix, protecting it from environmental breakdown. Modern chemical analysis has shown that heating the mixture to temperatures between 150 and 200 degrees Celsius initiates the bonding process. The temperature window is narrow. Too low and the indigo fails to embed properly. Too high and the organic component degrades. The ancient Maya achieved this balance consistently across multiple regions and centuries. The pigment appears on ceramics, murals, ritual objects, and sacrificial artifacts, maintaining its color despite tropical climate stress. In laboratory conditions, researchers have subjected Maya blue samples to acid baths, prolonged sunlight exposure, and extreme humidity. The pigment retains its structure where many modern paints would flake or fade. Attempts to replicate the compound are successful in controlled settings, but reproducing the precise ancient process, including mineral sourcing and preparation methods, remains partially speculative. Geological surveys indicate that specific palygorskite deposits used by the Maya were geographically limited. The clay was transported across trade networks, implying an organized supply chain for material production. What remains unclear is how the Maya identified the optimal thermal conditions without thermometers or chemical theory. Firing techniques likely relied on kiln color observation and empirical repetition. Yet the precision required to embed organic dye molecules into mineral channels suggests experimentation beyond decorative intent. The pigment was not purely aesthetic. It was symbolic, often associated with ritual and cosmology. In certain sacrificial contexts, objects coated in Maya blue were submerged in water and recovered centuries later with color intact. After the Spanish conquest, large-scale production of Maya blue declined. Colonial influence altered artistic materials and religious practices. The formula was not codified in written manuals accessible to Europeans. Over time, the knowledge dispersed. By the 20th century, scientists rediscovered the pigment's composition through spectroscopy and X-ray diffraction. Maya blue challenges assumptions about ancient chemistry. It represents a stable organic-inorganic hybrid material centuries before polymer science formalized such composites. Modern conservation scientists study it to improve long-term pigment durability and restoration work. If a civilization without molecular theory engineered a pigment capable of surviving millennia in hostile climates, what does that reveal about empirical experimentation in antiquity? And if such chemical knowledge was integrated into ritual systems rather than industrial expansion, how many other advanced material processes remain confined within cultural boundaries, never translated into broader technological development? The blue still shines on temple walls. It refuses to fade. And in its persistence, it hints at a scientific intuition embedded within tradition. one that endured in stone long after the society that mastered it was transformed. Top 9. The birch tar adhesive. The birch tar adhesive. In 2003, archaeologists excavating a site in central Italy uncovered something that did not resemble advanced technology at first glance. It was a fragment of stone tool hafted to wood, held together by a dark, hardened residue. Laboratory dating placed the artifact at nearly 200,000 years old. When chemists analyzed the residue, they discovered it was not random tree sap. It was birch tar, a synthetic polymer created through the controlled heating of bark in low oxygen conditions. The adhesive was strong, water-resistant, and chemically stable, and it had been manufactured by Neanderthals long before metallurgy, agriculture, or written language. Producing birch tar is not a trivial task. Simply burning bark does not yield usable adhesive. The process requires heating birch bark in an oxygen-restricted environment at temperatures between 340 and 400 degrees Celsius. Too much oxygen and the bark combusts into ash. Too little heat and the polymerization does not occur. Experimental archaeology teams attempting to recreate the process found that it demands deliberate engineering. Either bark must be sealed beneath sediment with a small vent or contained within a primitive kiln structure that allows distillation vapors to condense. In both scenarios, the tar drips downward and collects in a prepared cavity. The result is a thermoplastic adhesive with remarkable bonding strength. Mechanical testing on reconstructed birch tar shows tensile strengths comparable to certain modern epoxy resins. It adheres effectively to stone, bone, and wood. Once cooled, it resists water intrusion and moderate heat exposure. Microscopic examination of ancient samples indicates that prehistoric artisans sometimes mixed plant fibers or mineral fillers into the tar, increasing viscosity and mechanical durability. This suggests iterative refinement rather than accidental discovery. Additional finds across Europe confirm that tar production was not isolated. Hafted spear points and scrapers secured with polymer adhesives appear in multiple Paleolithic contexts. In some cases, residues reveal evidence of reheating and reapplication, indicating maintenance cycles. The adhesive was not a one-time innovation, it was a maintained technological practice. What unsettles researchers is the cognitive implication. Birch tar synthesis requires abstract thinking about cause and effect. It involves constructing a controlled environment to produce a material that does not naturally occur in its final form. This is not passive tool use. It is chemical engineering at a rudimentary yet deliberate level. Despite its effectiveness, birch tar production did not evolve into continuous polymer industries. With the advent of agriculture and later metallurgy, adhesive technology shifted toward pitch, resin, and eventually animal-based glues. Synthetic polymers would not reappear until the 19th and 20th centuries. The deep understanding required to produce consistent prehistoric tar faded into archaeological residue. Modern adhesives often rely on petroleum derivatives, requiring complex industrial infrastructure. Prehistoric polymers were produced from renewable organic material with minimal equipment. Their durability over tens of thousands of years demonstrates intrinsic chemical stability. Some recovered tar samples retain structural integrity after millennia underground. If Neanderthals mastered controlled polymerization processes without theoretical chemistry, what does that suggest about the depth of prehistoric experimentation? And if such knowledge existed so early, why did adhesive technology not expand into broader material science sooner? The residue on ancient tools is easy to overlook. It is dark, brittle, and unimpressive in isolation. But within that hardened polymer lies evidence that chemical innovation began far earlier than traditionally acknowledged. Long before steel blades or concrete domes, there was adhesive, a synthetic material binding stone to wood, and perhaps binding ideas across generations. Top 10. The Lost Ancient Alloys. The Lost Ancient Alloys. In the deserts of Anatolia, excavations at ancient Hittite sites uncovered slag heaps and furnace remains dating back to the 2nd millennium BC. Within these remnants were traces of metal processed at temperatures that challenge assumptions about Bronze Age capabilities. Archaeometallurgical studies indicate that certain alloys produced in these regions exhibited unusually high heat resistance and structural stability. These were not accidental mixtures of copper and tin. They were controlled formulations, that allowed tools and weapons to withstand repeated thermal stress, and the full methodology behind their production has not survived. Among the most intriguing examples are arsenical bronzes and specialized copper alloys discovered across the Near East. Arsenic, when added in precise quantities, increases hardness and enhances casting properties. However, it is volatile at high temperatures and toxic during smelting. Maintaining consistent arsenic content requires careful control of furnace conditions and ore selection. Too much arsenic in the alloy becomes brittle. Too little, and the mechanical advantage disappears. Metallurgical analysis of surviving artifacts reveals surprisingly stable arsenic concentrations, suggesting deliberate alloying rather than random contamination. Excavations in regions such as Timna in the Levant and sites associated with early Anatolian metallurgy show furnace designs capable of sustaining elevated temperatures through forced air systems using bellows. Experimental reconstructions have demonstrated that such furnaces could reach conditions sufficient to alter alloy phase behavior. Some artifacts display microstructures indicative of repeated thermal cycling without catastrophic grain growth. This implies an understanding, whether empirical or systematic, of how heat treatment affects internal metal composition. In addition to arsenical bronze, certain copper-tin alloys from ancient China in the Near East demonstrate resistance to deformation at high temperatures compared to typical Bronze Age metallurgy. The uniformity of casting and reduced porosity in select artifacts suggests advanced control over mold design and cooling rates. Modern metallurgists attempting to replicate these properties using reconstructed ancient furnaces achieve partial success but struggle to match the exact microstructural consistency observed in original samples. What remains missing is comprehensive documentation. While inscriptions detail royal conquests and tribute lists, they rarely describe furnace calibration or alloy ratios. Metallurgical knowledge likely resided within specialized guilds. Transmission depended on apprenticeship, not manuscript. When trade networks collapsed or political centers shifted, access to particular ore sources and skilled metallurgists diminished. Certain alloy traditions disappeared entirely from subsequent archaeological layers. Modern high-temperature alloys, such as those used in turbine blades and aerospace engineering, rely on carefully balanced compositions and precise thermal processing. Ancient alloys were simpler in elemental makeup, yet their performance in specific contexts suggests optimized formulations. The gap lies not in theoretical chemistry, but in controlled practice. If Bronze Age civilizations achieved reliable high-temperature alloy performance through empirical refinement, why did some of these formulations vanish instead of evolving continuously? Was it the scarcity of specific ores, the danger of arsenic exposure discouraging sustained production, or the loss of centralized expertise when empires fractured? The furnaces cooled, the bellows fell silent, slag remained buried beneath shifting sands. What survived are fragments of metal that still resist deformation centuries later. The progression of materials science is often depicted as steady advancement from primitive alloying to modern superalloys. Yet archaeological evidence hints at localized peaks of metallurgical precision that later decline. If high-temperature alloy control once existed in pockets of the ancient world, how many other material optimizations rose briefly and then disappeared with the societies that forged them? Across these 10 materials, from patterned blades to self-healing concrete, from nanoparticle glass to prehistoric polymers, a pattern emerges. Technological capability does not always advance in a straight line. It can surge, stabilize, and collapse. If ancient materials sometimes outperformed modern equivalents, the question is no longer whether they were impressive. The question is why their full potential was not carried forward. Across continents and millennia, the pattern repeats. A blade forged in medieval workshops displays nanoscale structures invisible to its makers. Concrete poured into Roman harbors grows stronger when fractured. An iron pillar resists corrosion for 16 centuries without protective coating. Glass infused with microscopic particles shifts color according to the angle of light. Pigment embedded in clay refuses to fade under tropical decay. Adhesives synthesized by prehistoric hands rival modern polymers. Alloys tempered in ancient furnaces endure heat and stress, beyond what their era should have allowed. Individually, each material can be explained. Empirical experimentation, favorable ore chemistry, environmental conditions. Isolated genius. But together, they reveal something more unsettling. Technological progress is not a clean upward line. It is a landscape of peaks and collapses. Knowledge can concentrate within small groups, perfected through repetition and guarded tradition. And when those groups disappear, the peak does not always become a foundation for the future. It can erode. Modern industry often optimizes for speed, scalability, and cost efficiency. Ancient workshops optimized for endurance within the limits of their environment. Their methods were slower, localized, and vulnerable to political disruption. When empires fell, trade routes fractured, or guilds dissolved, specialized material knowledge fragmented as well. What survived were objects, not instructions. The existence of these materials does not imply lost super-civilizations. It implies something subtler, that human capability is uneven, that discovery can precede theory, that refinement through hands-on practice can achieve outcomes rivaling later scientific frameworks. And that progress depends not only on invention, but on preservation. If materials stronger than modern equivalents once existed, their disappearance was not necessarily due to inferiority. It may have been due to fragility in transmission, a formula unwritten, an ore source exhausted, a furnace tradition interrupted. The artifacts remain. They do not advertise their sophistication. They endure quietly, resisting corrosion, decay, and fading color. And in their persistence, they ask a question that extends beyond metallurgy. If technological peaks can vanish once, could they vanish again? If these stories of lost mastery changed how you perceive the progress of civilization, subscribe to our channel. We are excavating the history that time tried to erase. Cultivate the future. The next vault of knowledge will open soon. Like this video to join the search for the truth.